All right, we've got some good stuff to go over today, so let's get right into it. Your next homework assignment's due on Thursday the 27th. Boy, could that be right, that you've got that much time to your next assignment? That doesn't seem like me at all. That's got to be a mistake. But did you just turn something in this morning? Yeah. I guess that explains it. All right, well, I'll try and remedy that in the future. It is going to be busy on that day, though, because we've got our first exam on Thursday the 27th. And so the equation sheet is already posted online, and I think, if I'm not mistaken, I also provided you with kind of an example exam. I breached one of my old ones and put it out there for you to get a feel mainly on like the level of difficulty and kind of like what my style is on tests. So if you look at that exam, you'll see that there's only 3 questions, and there's a lot of calculations that go into each one of those questions, and so it's the sort of thing where you really got to be careful about avoiding mistakes. And one of the bits of advice I've given you before is to always include your units as you're doing the calculations, and I found that's one of the really effective ways to avoid mistakes. The students who don't write their units are generally more prone to making mistakes, and occasionally you'll write down the units and then it'll remind you that maybe you've used the wrong equation, or that you've used kilonewtons when you should use newtons, or whatever the case may be. So that will be covering through classes 1 through 11. So it's going to include everything up to a week from today's lecture will also be included in the material that's going to be on that exam. So it'll be the entirety of chapters 2 and 3. Now, last time we talked about hydrostatic forces on flat surfaces, and we looked at all the different ways we could orient a flat surface: a vertically oriented flat surface, at an angle, horizontally oriented flat surface. And so what that prepares us for is how to tackle the calculations related to forces on curved surfaces. So are there any questions before we get into that? Did everybody get my email about, for the lab tomorrow, installing water gems? Okay, yeah, that's really important. You'll just sort of sit and watch everyone else have fun if you don't bring water gems tomorrow. So don't be left out. It's going to be a real party. We're going to be playing with water gems. It's a great program that actually you'll use a lot in hydraulic engineering next semester. But this is just sort of the earliest taste that we can give you with water gems. So please bring your computer to class tomorrow. All right, so hydrostatic forces on curved surfaces. I know that you're already familiar with the idea of projections. And let's see, can I turn on the cooler? Nope, I'm locked out. All right. I don't have the brain power to turn on the cooler. They got to lock us out. All right, so a projection is sort of a 2D representation of a 3D object. And so just an illustration, I think at one point everybody has done this sort of thing where you put your hands in front of a flashlight and you look at the shadows that it projects. And so that's an example of a 3D object and the shape that it traces when you're doing a projection. So a more complicated engineering drawing. When I was in your position, when I was an undergraduate student, we actually had 2 semesters of CAD, and each of them were 3 credit hours. So I had 6 hours of CAD, and I think you guys have, what, 2? So we did the first semester hand drawings and the second semester CAD. And so we were actually using like this old-timey stuff called vellum, which is like kind of a plastic that you draw onto with these specialized inks. So one of the things that blew my mind when I first doing that sort of thing was looking at an object that has tapers and angles and is only cut to a certain depth, and then trying to find out how that would look from a certain direction, and looking at it from the front, looking at it from the side. And it was something, frankly, I was really terrible at first. Sometimes the spatial skills that it takes to visualize what something looks like from different directions just doesn't come naturally, and it didn't come naturally to me. Now, the reason why we have to think about projections is that sometimes these 3-dimensional shapes, we have to think about their 2-dimensional projections in order to calculate the hydrostatic forces. So let me walk you through it step by step. Let's say that we have a tank of water that is enclosed at the bottom with a curved gate. And so speaking of trying to think about things in 3 dimensions, so this is like a flat metal plate that has been bent, and so that now we're just looking at it at a side angle. It looks like a quarter circle if we were to continue the curve all the way around. So it's a quarter circle looking at it from the side. But if we want to know what are the hydrostatic forces that are acting on this surface, think about really what is causing those forces. What we know is that it's a distribution of pressure that's causing those forces. And so we've got a gate that's curved and has varying depth, and so the deeper we go, the higher the pressure is. Up here at this top edge of the gate, the pressure is relatively speaking lower than if we go a little bit deeper into the fluid. And the other thing that's tricky is that the direction of the forces is perpendicular to the surface itself. We talked a little bit about that in the lab last Wednesday when we were working with that curved annulus. So in this case, there is a distribution of pressure and a change in direction of the pressure. And so what we're trying to find out is what's the equivalent hydrostatic force and where is it? So if we were going to say force is pressure times area, we've got a bunch of little pressures, and we could divide that curved gate, if we were looking at it from the front, it would look like this. We could divide it up into little elements, these tiny little segments, and say, what's the pressure acting over that element? Pressure times area. And then we'd go down where the pressure is a bit higher, and we'd say, what's the pressure times area there? And so we want to integrate all of that and then just find out the one resultant force that's acting on that gate. And we want to know not only the magnitude, but also the direction and the location. The hydrostatic force. So it's magnitude, direction, and location. And so in order to do that, some of the things that we have to consider when we have a drawing is this curved surface that we're trying to find the forces. What is its shape? What does it actually look like in 3 dimensions? Now it seems obvious here because it's just a curved gate. But sometimes we'll have hemispheres so that if you look at it from the front, it just looks like a circle. And so it could be that it's a circular gate, or it could be hemispherical. You have to look at the problem statement, look at it from another view to know for sure. And the forces that would be generated are going to be wildly different if it's a hemisphere shape versus a circular shape. So you have to think about what is the shape and the geometry of the curve. How deep is it located underneath the water level? Because, of course, we know that if we're going to be calculating the pressure, then pressure is delta H times gamma. So we need to know beneath the surface how deep are we talking about, because the pressure depends on that. Where does the curve intersect the straight surfaces? And so there will be dimensions that tell us how deep it is from the water surface down to the beginning of the curve, but then also we need to know how deep it is to the bottom, and what is the radius of curvature here. So this curve could be described in terms of the radius point about which that curve is generated, and the reason why that's important is we're going to be looking at the horizontal component of this hydrostatic force and the vertical component. So the resultant is at an angle. If I just erase these, this pressure distribution, and all I leave behind now is the single resultant hydrostatic force. So here's the hydrostatic force. Well, there's a vertical component to that, and there's a horizontal component to that. And the way that we find the overall resultant hydrostatic force is we solve for the 2 pieces. The force vertical and force horizontal. So is everybody with me so far? Get the main idea? All right. So it all starts with looking at the sketch. And so the sketch may have dimensions on it, like this. Remember those questions that it asked on the previous slide. So when we have the dimensions here, we can tell just by sort of inspection the shape of this is a quarter circle when we look at it from the side view. And we want to know what's the force that's acting on this surface, AB. And we can see that it's from the water surface down to the beginning of the curve is 4 meters. So that would be an important dimension. And every problem you're going to face is a little bit different sketch, but you should ask these same questions. What's the shape of the curve? How deep is the curve? Now, in this case, we can see from this horizontal width of 2 meters that also is what defines the radius of curvature, and also how deep it is from A to C. Because if CB is 2 meters, then that same distance applies to CA. And it's important to label these different points, because what we're going to do is break the element of water that's above the curved gate. We're going to break it up into pieces. And so I'll talk about that there's a rectangle of water, or actually it's kind of box-shaped, because we'll start thinking about the depth into the page, and then this quarter circle. Now this representation shows the vertical forces and the horizontal forces. And it's given that this surface is 1 meter into the page. And so that's kind of like the depth parameter, like how we're looking in this side view. The AB is a curved plate that from C to A is 2 meters, but the distance into the page is 1. And so we could calculate the area of the projected surface. And to find the force balance here, to find the overall force that's acting on the gate, and therefore how much would we have to apply a force F to resist that force. And so this external force that's shown outside of the water, this represents the force that would be required to hold the system steady, to make sure that we keep it in equilibrium, that this plate doesn't fall out because of the weight of the water above it and these horizontal hydrostatic forces. Those are the two things that comprise the overall net hydrostatic force that's acting at an angle. Okay, so what we're going to do is go through the steps of calculating what is the weight of the water in this element B, C, D, E. So if we think about what that, like what's the shape of that element, it's going to be a shape that has a width of 2 meters, a height of 4 meters, and then into the page we have this 1 meter depth, and so there's water in that element. And the vertical forces, we can see, it's going to be the weight of the water. And so let me transfer this sketch onto the whiteboard. And let's see, we've got this, the curve continues upward. Here's the water. Okay, it's A, B, C, D, E. And it's 4 meters and 2 meters. All right. Actually, okay, what I've done here on this slide is we've got these steps that we need to find the vertical forces, that is this first element, BC. This is B, C, D, E. Okay, then there's this other shape that looks like this. Okay, and that is A, B, C. The way that we calculate those is pretty easy. It's the force is the weight of the water. And that's only talking about the vertical force. And so it would be the volume times gamma. Okay, so that's how we get our vertical forces. The horizontal force, this F sub h, that is going to be determined by considering this curved surface as though it's projected vertically. And so what does the vertical projection of that curved surface look like? So if we had this gate that has a height of 2 meters from edge to edge vertically, and we're shining a light on it, think about what is the shadow that would be projected here at AC for that curved surface. Well, it would look, if we just were looking at it from the side, it would look like a gate that has 1 meter width and 2 meter height. So we're going to pretend like there's a flat gate there at AC that has the dimensions 2 meters high, 1 meter wide, and we're going to calculate the hydrostatic forces on that vertical projection. So that's what it's hinting at here in step 1, F sub h. Find the horizontal hydrostatic force as though there's a force acting on the vertical projection of AB. So we go through the same steps that we have before. Namely, you find the force by P bar A. And of course, P bar means the pressure at the centroid. So that is delta H times gamma times the area. And so you're going to have to consider how deep it is from the water surface to the centroid of that projection. And so there's this imaginary rectangular gate at AC that's the projection of the curved surface. So if it's just a rectangular gate, that means that the centroid is half the way down. So it's here, this is the delta H, from the centroid back up to the water surface. All right, so rather than me do the calculations on the whiteboard, particularly because my marker seems to be dying out, what I'm going to do is I'm going to pause from talking, give you some time to work together with your classmates and calculate what is this horizontal force, what are the vertical forces at B, C, D, E, what's the vertical force, this W is talking about the weight of the water due to A, B, C, so just that quarter circle element, and then the overall component Fx and Fy. So that's talking about here what's the horizontal component of the external force that has to be applied, and what's the vertical component of that external force that needs to be applied. So the Fx will be this one, and Fy will be the vertical. And then once you go through that and calculate 1 through 6, then we'll discuss how to calculate where the force is located and what its direction is. For now, I'm just going to ask you to calculate the magnitudes. If you want to start checking on some of your calculations, I've got the solution up on the screen there. Okay, so let's just talk through it to make sure that we're all on the same page. So the vertical projection of the curved surface. You're going to hear me say that phrase over and over and over. So it's critical that you understand what I mean by the vertical projection. So that means we've got some curve. In this case, it's just a plate that's been bent. So we've got a curved surface, but we want to know the vertical projection. So in other words, what is the vertical component of that shape? In this case, the vertical component of it is a rectangle with 2 meters of height and 1 meter of width. So what we do to calculate the magnitude of the horizontal component of the hydrostatic force, the horizontal component of the hydrostatic force is you find out what is this vertical projection. And so in this case, it's a rectangle. And since it has 2 meters height, that center of area is 1 meter from the bottom edge. And the previous dimensions that we saw on the last slide was saying it's 5 meters from the water surface down to the top edge, and then 1 more meter to the centroid. So the delta H should be 5. Find the pressure at the centroid with delta H times gamma. Multiply that by the area, not of the actual surface. It's the area of the projection. So it's going to be 1 by 2. Okay, so the horizontal component of hydrostatic force is 98,100 newtons. Any question about this first part? This is one of those cases where it'll really be valuable if you take the time to review your textbook after today's lecture, because there's some drawings in the book that give you practice looking at things and interpreting what the vertical projection is going to be. Of course, you'll get some of that practice in the homework assignment as well. Okay, now the vertical force, F sub V, that it was talking about here, that's referring to that box above the quarter circle, and we want to know the volume and therefore the weight of the water that causes that vertical force. And so it's 2 by 1 by 4. The weight of the water there, 78,480 newtons. And then we do something similar with that quarter circle shape. So we'd take the area of a circle and divide it into 4. So it's just a quarter of the circle. And then once we find that area, multiply it by 1 meter to get the volume of that shape. So it's the area of the shape multiplied by 1 to give it its volume dimension, then multiplied by gamma till it goes from volume to weight. So the overall vertical force is going to be the sum of those two components, F sub V and W together. Any questions so far on this? Okay, so we sum the horizontal forces and the vertical forces and find the resultant. So you can see this external force that we have to apply, it's going to have to resist the horizontal hydrostatic force, F sub x, and the sum of the vertical forces. So we add the two vertical forces together and 109. The horizontal was the 98,000, and then the resultant F is going to be the square root of the sum of the squares. So 146,870 newtons. Okay, so that's the process for finding the magnitude. Now, finding the location and the direction of the forces gets a little bit more complicated. So the way that we can start there is by thinking about where are the forces that we've just calculated, where are they located? We can start with the horizontal force. And the horizontal force, remember, is all based on the vertical projection of the curved surface. And so we just pretend like there's a gate in the water, and we want to find out where is the location of the force acting on that projected gate. So we've got a gate here that's vertically oriented, which is nice. Here's the centroid. We previously determined that the centroid delta H is 5 meters down to where that force is located. So where basically we're at, what we're asking is this horizontal force component, F sub H, what is its location? And we know that's YCP. YCP is the depth to the center of pressure. That's what CP stands for. The center of pressure is where the equivalent hydrostatic force is located. So what is YCP? And you'll remember that the calculations that we do for that, we have to know y bar, and since it's vertically oriented, y bar equals delta H. That makes things a little bit easier for us. We have to have the area moment of inertia, I, and remember I is AB cubed divided by 12, and so A is the width parameter, and of our projection that width is 1 meter and B is 2 meters. So AB cubed divided by 12 is just talking about the area moment of inertia, not of the actual curved gate, but the area moment of inertia of the vertical projection. So then that's how we say what is the location of the hydrostatic force, the horizontal component of the hydrostatic force, is by describing the YCP. The way that we calculate the location of the vertical forces is a little bit more complicated. It's just sort of like a weighted average. And so if we go back to this sketch, the original drawing that was given in the problem statement, you can see that they've located this F sub V in the middle between B and C. That's intentional. They put it in between B and C because that is, horizontally speaking, where the force is located, in the middle between the two edges. So in other words, if you had that element of water, that rectangle B, C, D, E, if you're going to try and balance it, the balance point would be in the middle. If we're talking like side to side, its location. So the B, C, D, E, it's just in the middle, F sub V. And let's start measuring things from this edge, from the edge CD. So we would say it's 1 meter distance from that left edge to where the vertical force F sub V is located. Now consider that quarter circle. Look at the drawing and where they put W. It's not exactly in the middle, is it? It looks like they've shifted it slightly. The location of this force vector, W, is to the left of F sub V. Why do you suppose they put it there? What are they hinting at?
Where the centroid of that shape is.
Perfect. Yeah, the centroid of that shape. And so why is the centroid of that shape to the left of the midpoint? For the rectangle, it was halfway between the left and the right. Why is it that it's shifted to the left for this quarter circle? Yeah, it's not symmetric. And so the asymmetry is that some of the area is missing from the right side. Like if you just look at where's the center of area, since we've got this, I really wish I could draw on that. It's driving me crazy, so I'll just draw on the whiteboard, I guess. So all of this area that's missing brings the location from the center a little bit to the left. So what we need is a formula that describes the location of the centroid for a quarter circle. I thought I had one of those formulas. I do. I thought it was on the slide, but I'll give it to you. The centroid for a quarter circle, C sub x, is 4r divided by 3 pi. Okay, so what that's saying is here's our radius, r, the distance from the center point out to the outside edge, and we can measure how far it is from that left edge with the formula 4r divided by 3 pi. And so if we just substitute in the known values for that, it's 0.8488. So what that's talking about is how far from the left edge to where the center of area is. And we would expect that it's going to be less than 1, because remember, it was 1 to get to the middle from the two sides. And so if the overall r dimension is 2 meters, and we're missing some area off the right side, then that force is going to be closer to the left side than it is to the right side. So just reality check. You'll always want to just make sure that this is matching reasonableness. Since this is less than 1, that seems to match what our expectations would be. So what we need to do now is come up with an overall weighted average of those two forces when we combine them together. Because we've got F sub v, which is large, a pretty big force, in the middle, and we've got W, which is a little bit left of middle. So when we combine those two forces together, where is the net resulting vertical force? Well, we can't just average it. You know, like 1 from the left edge to F sub v and 0.8488. It wouldn't be reasonable to just do a simple average, you know, combine them and divide by 2. And the flaw with that thinking would be, well, the vertical force, F sub v, of that rectangular shape, it should count for more because it's larger. And so that's what a weighted average does, is it takes into account the relative size of each. And so this weighted average, what I'm saying is we've got this big force of 78,000 newtons, which is 1 meter from the edge. And then we've got this relatively smaller force of 30,819 newtons, and it's 0.8488 meters from the edge. And so if we multiply it by the weighting factor, the location, 1 meter, 0.8488, the relative location by the weighting factor, and then divide by the sum of the forces, which is the total weighting factor, then that's just a way of coming up with the average location of both forces when combined. So if you're measuring from the left edge, it's going to be somewhere between 0.8488 and 1. And that's what this does, is it tells us how far between those 2 points when you combine the forces together. So it's a weighted average. It's easy to get lost in the details, so let's take a step back and just think about overall, what did this example ask and what did we calculate? We wanted to know what's the magnitude of the hydrostatic force that has to be applied to resist that the water that's acting on the gate. And so the magnitude is going to take both the vertical and the horizontal into account. But for a variety of reasons, we want to know of those components, of the vertical component, of the horizontal component, where are they located? So in all the problems you work, for the horizontal forces, you'll use the method of y bar and YCP. But then for the vertical forces, you'll have to do a little bit of weighted averages and maybe geometry type stuff to find out where the force is located. Are there any questions about this example before we take a look at the next one? Okay. So, hydrostatic forces on curved surfaces. Let's say that we have a curved gate. This time it is, I guess this is convex rather than concave. The other one was concave. This is convex, and so that means that the curvature is extending into the water. So we want to find out this force F. What's the magnitude of that required to open up the gate? And it says it's 4 meters wide, so that's talking about this dimension into the page or into the screen is 4 meters wide. But then we can see that this radius of curvature is 3 meters. So what does the projection look like? What's the shape of the vertical projection? Yeah, so it's rectangular. What are the dimensions of the vertical projection?
4 meters wide, 3 meters tall.
Perfect. 3 meters tall, 4 meters wide. This is the vertical projection. And we use that to calculate the hydrostatic forces that are in the horizontal. So we want to find out the force required to open the gate. And if we think about what are the forces, where are they, how much are they, what we've got is it's going to be, in the end, a moment analysis problem, where we've got this force F that we want to find out how big is it. So there's going to be vertical forces and horizontal forces that are trying to close the gate. So those are both working in the counterclockwise direction. So there is a horizontal force that's pushing to close the gate this way. There's a vertical force from the weight of the water above it that is trying to keep the gate closed. And what we need to do is we need to find out what's the magnitude and the location of both of those so that we can do this moment analysis part of the problem and calculate the overall force. Okay, so what I've done in this slide is I've said, imagine that what we want to do is find the forces and where they're located. And so there's going to be a box of water above the gate, this element A, and then we want to find the weight of the water that is above the curve. So that's element C. Does everybody see how what I'm doing here is I'm saying, consider this shape on the left, and let's break it up into pieces. We've got the 2 meters from the water surface down to the beginning of the hinge. So that's this 2 meters. And a 4 meter wide gate. Why am I saying here that it's 3 meters? Oh, no. Okay. This is not a side view. That's why. Yeah. All right. So the 3 meters is going to come into play when we consider taking out this element that doesn't apply. So it's a little bit different from the last one where we had the shape of the water was a quarter circle, that curved component, because now the weight of the water that's immediately above the gate, that isn't a quarter circle, but it is a rectangle minus a quarter circle. So it's this shape right here, but we need to find the weight of the water in that shape C to find out the vertical forces overall. All right, so the first thing that we do in this is we take a look at the element A. So let's first have the force A is going to be the volume times gamma. And so you can just by sort of inspection see that that is going to have 2 meters by 3 meters by 4 meters as its volume. Okay, so 2 is the height of this box. 3 is the width, and then it's 4 meters into the page. And then we have to multiply it by 9810 newtons per meter cubed. Okay, so the net volume is 24 meters cubed, and that's just talking about this element A. So the force of the weight of the water of element A is 235,440 newtons. Okay, now in order to calculate what is the weight of the water of element C, what I'm going to suggest is that first we calculate B. So B is the whole rectangle, that is all of the water that would be here if we had it going from the hinge all the way over to the edge and down and then back again. So the total water before we extract out the quarter circle that isn't actually there. So we want to find out what is the volume of water in B, and then we're going to subtract out the quarter circle D, and what's left behind is C. So in other words, the reason why we're doing this is we're going to say C is B minus D. So again, let me just go back to showing you what was B. B is all of the water that is beneath the hinge over to A and then 4 meters into the page. So there's this rectangle of water, B, and the reason why we calculate it is it's kind of an intermediate step. Once we know B and we've calculated D, then we can calculate the weight of the water by subtraction. All right, so B, the volume there is, it's 3 by 3 by 4, so 36 cubic meters. D is a quarter circle, so it is 1/4 of pi r squared. So pi 3 meters squared. So that gives us the area, and then we multiply that by the depth into the page of 4 meters, and that provides the volume. So the volume there is 28.274 cubic meters. And so then C is the difference between the two. So it's 36 cubic meters minus 28.274 cubic meters. So 7.726 cubic meters is the volume. Just of this little thin strip of water that's immediately above the gate. So over here, we've said we'll break it up into the rectangular component and then this curved shape. And that's the volume of the water, so we can calculate the weight of the water. I'm going to call it force C is that 7.726 cubic meters multiplied by 9810 newtons per meter cubed. So is everyone with me so far? All right, so what I'm going to ask you to do, and this is, I know this is a leap because you've just started thinking about these force locations, is find out where is the overall vertical force location. So we've got the force of A is in the middle, and then the force of C is some distance from the edge. Well, the way that we calculate where that force at C is located is by saying, remember that C and D together are B. So B is in the middle. The location of this force B, it's in the middle. And so it has to be in the middle as a result of averaging its two components. So if B is in the middle, and we know that we can calculate the location of D with this formula, then the only unknown will be how far it is from the edge to where C is located. So that's what I'm going to do in this next step, is I'm going to say we've got this element B, which was 36 cubic meters. Let's weight it by volume. So there was 36 cubic meters is the weighting factor, and it should be located 1.5 meters from the edge if we're measuring from this right side. So 1.5 meters from this edge, and the overall volume was 3 by 3 by 4. Okay, so B is the combination of C and D. So that is the result of combining the volume of element D. So previously we found that element D had a volume of 28.274 cubic meters, and then its location is going to be 4 times R, which is 3 meters, divided by 3 pi, and then adding this volume of C, which we know the volume but we don't know the location. So 7.726 cubic meters, but the question is, where is it located? And I'm going to call that XCP for element C. So XCP is the horizontal center of pressure. So we've got this equation and only one unknown, how far it is from the right edge to where that force is located. So if we go through and do the calculations, what we'll find is that the XCP of C is 2.33 meters. All right, so that is, if we measure from the right side, it's 2.33 meters to where that equivalent force is acting. Okay, so I'm going to pause for a moment and give you a chance to copy this down or double check the calculations, think it over. I'll bring the solution up on the screen too, just to make sure that it gets recorded. I've taught this class enough times to know that a lot of students leave this lecture shaking their heads saying, I really don't think I got it. So if you're in that position, I think that time, hopefully, it's the sort of thing where it trickles into the brain rather than just going in at the normal rate. Like, you have to kind of prove to yourself that if you want to find the location of that small piece that's immediately above the gate, this element C, I don't know, the best way I've been able to describe it is consider the overall box B and then the components that would make it. So the whole is comprised of the parts, and we know the parts are C and D. D doesn't actually have any water. That's beneath the gate where it's in contact with air. So we're just trying to find out how far it is to the center of area for C. And so this is the approach we can use to calculate it. So you'll get some more practice on this with the homework. So the reason why it's important to know these is we were trying to find out the force required to open up the gate, right? So now we know the magnitude and location of the two vertical forces. There's the vertical force that is due to that smaller piece, C, and then there's the big piece, A. So we know the location and the magnitude of each. So we know that it's in the middle for force A, and how far it is from this hinge. And by the way, that dimension is our moment distance from B. Okay, now there's also the horizontal forces that are acting to keep the gate closed. If here's the gate and it's curved like that, then there was this F sub C, which is trying to close it, and then there's force of A that's trying to close it. There's also the horizontal hydrostatic forces that are trying to close the gate. And so we have to calculate those as well. That's less tricky because all we have to do is find the depth of the centroid. So let's go back to the sketch and think, what does the vertical projection look like? Well, it's this rectangle that is 4 meters wide, 3 meters tall. The centroid, how far is it up to the water surface from the centroid? Okay, so it's 2 meters plus another 1.5 to get to the centroid. So it's 3.5 meters is the delta H and also the y bar. Since it's vertically oriented, y bar and delta H are the same. So the horizontal force, F sub H, to find the magnitude, it's the pressure at the centroid, P bar times the area. So in other words, delta H times gamma times the area. So 3.5 meters times 9810 newtons per meter cubed times the area, which is 3 by 4, so 12 square meters. So the magnitude of that force is 412,020 newtons. So that's this. And it's closing the gate, and we want to know what is the location of it. So YCP is going to be y bar plus I divided by y bar A. So y bar is 3.5 meters plus I. So I guess off here in the margins, we will have I is 4 meters by 3 meters cubed divided by 12. Remember that we always cube the vertical parameter for a rectangle like this. So the area moment of inertia is 9 meters to the fourth. So that's what we'll substitute in here for I. 9 meters to the fourth, 3.5 meters multiplied by the area of 12 meters squared. So YCP is 3.7143 meters. So that tells us how far from the water surface down to where that force is located. 3.7143 meters is from the water surface to the point of application. But ultimately what we're doing is a moment analysis. So what we want to know really is how far is it from that edge down to where the force is located. So if we think in terms of the moment analysis, then what forces are acting to move the gate counterclockwise, to push it closed? Well, there is F sub A. So we found that that was 235,440 newtons. And it's acting at a distance of 1.5 meters from that edge. So that's the moment distance. And then there's also the force C. So that's 75,789 newtons. And it's acting at a distance of 2.33 meters from the hinge. That's how far over it is. And then also acting in the counterclockwise direction is the F sub H that we just calculated. So 412 412,020 newtons, and then the distance is 1.7143 meters. If we subtract out the 2 meters from the water surface to the hinge. So we just want to know how far below the hinge is that, because that's the effective moment distance. So all of that is going to be balanced out by this force F. Force F, and it is acting at a distance of 3 meters. That's the distance from the hinge. 3 meters. So if we stop and calculate for what F is going to be, then the force required to open up that gate should be 412 kilonewtons. And so just to summarize, there's 3 forces that are acting to keep the gate closed. The weight of the water that was in element A, the weight of the water that was in element C. Both of those are acting straight down, but we have to know exactly where they're located in order to know the moment distance. There's the horizontal force that's pushing on the gate, and we calculate that magnitude by considering the vertical projection. Its location is determined by the YCP formula. And then the force that's opening the gate is a 3 meter distance away. So, yes?
What steps do you take to find, for force C acted from the vertical axis?
To find the 2.33?
Yeah.
All right. So what we did there, that was the whole thing where I was saying consider element B, which is all of the water that is down here, or that would be there if the gate wasn't in place. So B is the sum. Now consider the pieces. There's where there's water and where there's air. And so that 2.33 was this unknown distance that I said it's the weighted average B that allows us to calculate the 2 components. So that was, if I show you on the slide here, this vertical force location step where we said that if element B acts in the middle, it acts in the middle because it's the average of the 2 pieces. It's the average of piece D and C. And so C was the only unknown in that equation, and that's how we found how far over. Now it turns out there actually is a formula for the center of area of a shape like this. I don't know the name of that shape. Somebody looked it up once and found the centroid formula for it. But I think it's still, even though you could find the formula for that centroid, it's important to refresh your memory of this process of superposition, that you can find some unknown parameter by breaking it up into its component pieces. Okay. Let's say, what if we had a gate that was at the bottom of a tank like this, and it's irregularly shaped. And so you don't exactly know how far it is, like the vertical distance down to a certain location. So you can't do it as simply as pressure times area. The interesting thing is that the forces, in this case, you can find the force required to hold this gate is just the weight of the water that's above it. But in the same way, the forces that are acting upward on this gate are equal to the weight of the water that would have been above it if this gate wasn't in place. And so what I'm saying is, what you can do is you can find out what is the volume of water if you extend this imaginary surface all the way up to where the water line is. The vertical forces is equal to the weight that would have filled up that volume. So you have a homework problem where this actually comes into play, where you're having to calculate the weight of the water that would have been in place if the gate wasn't holding it back. Just wanted to put that in your mind. So let's look at some key ideas for the homework assignment. Even though you've still got plenty of time to work on it, you can get started early while some of these things are kind of fresh in your mind. You need to find the magnitude, location, and direction of forces on the gate. So this first vertical force, you're going to find it out by the weight of the water that would have been above this gate. So if you think, where is the water pushing? The water is pushing upward and towards the left. And so the vertical component of the overall resultant hydrostatic force, the vertical component, is the weight of the water that would be above that gate. Now you need to find the location, and so you'll use that weighted average approach that we used for both of our examples today of, you break it up into pieces. There's the quarter circle piece, there's the rectangular piece, and the location of the rectangular piece is in the middle. The location of the quarter circle piece is shifted a little bit towards the left. And then you'll find the horizontal forces by the vertical projection. So you think about, if you shine a light on this curved surface, what is the shape that the shadow makes? And so it's going to be a rectangular shape. If you want to calculate the angle that the force is making, so the relative distribution of horizontal and vertical forces, the tangent of that angle is the horizontal divided by the vertical forces. But as long as you find the magnitude, location, and the direction of the forces on the gate, then you will have completed the requirements of that problem. The other thing I wanted to show you on this problem is you've got forces that are acting on a hemisphere. This is kind of like a plug that is in place to prevent water from leaking out of a hole. This O-ring is like a circular rubber gasket that goes in 3 dimensions. If you think about it, it's looped all the way around, and it's there to make sure that the water doesn't leak out. And so to find the forces, here all they want is the magnitude of the forces, but not the location. So emphasis here that it just wants the magnitude of the horizontal and the vertical forces. So for the horizontal, you have to think about, what does the vertical projection look like of that hemisphere? So it's going to be a circle. And they give you the dimensions of the O-ring for a reason, because that hemisphere, there's water that's acting on it from both sides until the O-ring kind of traps the water out. So we've got, let me draw it like this. So there's water that's acting this way horizontally. But for part of it, there's also a little bit of pressure until you get to the O-ring that's canceling it out. So when you find that circle of water that is the circle shape that the water is actually acting on, you'll use the 0.2 meter dimension rather than the physical radius of that hemisphere, because the water is underneath that lip. Now the vertical force here, we're going to get into more of this buoyancy idea, but you can find out how hard the water is pushing that part upward by calculating the weight of the water that's displaced by the part. So vertical forces upward for this, where the water would have been if that hemisphere wasn't in place. Well, this is half of a sphere, and I wanted to remind you, this is the formula for a sphere. So you find the volume of water displaced and multiply it by the unit weight. That'll tell you the weight of the water displaced. All right. So that's all I've got for you today. I'll see you on Thursday.